What if passing the test is not enough? In reliability engineering, we often place a great deal of confidence in laboratory validation. We test, measure, analyze, and document. And when the product passes, we naturally assume it's ready for the field. But what happens when a product passes the lab test and still fails in the hands of the customer? Welcome, or hopefully welcome back to Reliability Matters. I'm Mike Konrad. Today we're going to explore the gap between laboratory reliability testing and actual field performance. It is a gap that can be costly, frustrating, and sometimes difficult to explain. Products can perform well under controlled test conditions, yet still experience unexpected failures when exposed to real users, real environments, real surface conditions, and real-world variability. My guest today is Dr. Nishith Kumar Reddy Gorla of Core ITS LLC. Dr. Gorla's work focuses on systems-level reliability testing, field reliability alignment, reliability growth, and test-to-field correlation for complex products. His recent paper, System-Level Test Case Design for Field Reliability Alignment in Complex Products, that's a mouthful, looks at why functional reliability test methods may miss important field failure modes. More importantly, he proposes a broader approach to test case design that considers not just the product design, but also actual use conditions, field failure data, end user behavior, service procedures, manufacturing variation, consumables, and product interfaces. This is an important conversation because reliability is not simply about passing a test. It's about understanding how a product behaves in the real world where variables interact. Users behave unpredictably, environments change, and failure mechanisms may not appear until the system is challenged in realistic ways. If you design, build, test, specify, or depend on complex products, this discussion should be especially relevant. Today, we'll talk about why products sometimes pass in the lab but fail in the field, how better system-level test cases can improve field correlation, and what reliability professionals can do to create test methods that more accurately reflect real-world performance. And it all begins right now. Stick around. This is going to be good.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Konrad.
Nishith, welcome to Reliability Matters. I'm happy to have you here today.
I'm pleasure to participate in this podcast. So it was nice introduction as well.
Well, you have a lot of nice work you've done, and this particular topic is perfect for the show because reliability often somewhere in there is testing and reliability assurance, not reliability assumptions, reliability assurance.
Exactly.
And sometimes it becomes assumptions. So we're gonna talk about that. Before we get into the technical details of all this, can you tell us about your background and how you became focused on reliability engineering and system-level test design? How'd you get here?
So actually, my background is a little different than reliability. So I have my doctoral degree in aerospace engineering from University of Texas at Arlington. Then I was looking for opportunities to move to aerospace background. Then I had a little, tough time or challenging days getting to the aerospace field. Then I was looking like what would be the next, future step I would like to take, which will align with my, background and those things. Then I started interested in medical devices. Then I was joined as a verification and validation engineer. So then I was more interested in reliability and stuff. Then I get into the reliability work. Then it was a new product development. That stage, during the initial days, it was nothing in our company on the reliability. Then when I joined, we started reliability testing, creating from the reliability goal, from the reliability plan to all DFR processes. And I was more focusing on how we design the test and how we design the test case, and those kind of things are very critical in the reliability field. So then we should have an approach, right? So otherwise you if you want to test some random failure for anything else, then we don't know like whether it's going to happen in the field or not. And it should be realistic, right?
Right.
So then we created an approach for the reliability test design. So it, since for example, right, so if you take a motor, AC motor as an example, so you have n number of failure modes. You don't know like which one to test, right? So we earlier we have like earlier we had traditional approaches like based on the expert opinion or follow the like military handbooks or any kind of standard. So we refer those handbooks, and then we document failure modes, and then we move forward. But how this is realistic for, so the products may be different. I mean, you can see the similar components or similar parts from different handbooks and those things, but how it will be suitable to your actual product or application, so that is
Yeah.
the matter, right?
Yeah.
So then we thought of like, why can't we implement or create an approach based on critical failure mode prioritization method, right? So instead of going for like traditional approaches, we can create our own approach that will reflect in the field test to field correlation very close, about like 90 to 95%. So whatever you are seeing in the lab, so you can expect them in the field as well. So if you test very carefully, or if you test as per the failure modes what we determine from the approach, that will not be in anymore in the field. So you can reduce the downtime. You can provide the customer satisfaction. You can basically releasing the reliable product to the field.
It's
So
interesting. You're known now as a reliability expert. Your
yeah,
doctorate was in aerospace,
aerospace. Yeah,
and that's not specifically reliability, although a lot of reliability goes
yeah,
along with that.
yeah,
But it's interesting that the two career paths that you
yeah.
took, one was
Mhm.
aerospace, which is highly reliant on reliability, and the other is medical,
Yeah.
which is highly reliant on reliability. So reliability
Yeah.
seems to be attracting you. Now, when you started working within the reliability part of
Mhm.
those industries, did you do so because you saw a deficit somewhere? Did you see a disconnect? Were you trying to solve a problem, or
Yeah.
what drew you to that?
Exactly, like, so we had a previous product in the field already before I joined the company, or before I start working in the reliability field. So we have seen multiple failures for the previous product. So then we go back and check like what happened. Then we realize like we don't have a defined process, or the way we test the products, it's different, or we followed some traditional process, or which may not help product to be successful in the field. So then we decided like we found the gap actually. So we haven't followed the we haven't followed the exact, correct approach to make things will pass in the field. So that's where the connection missed, and then we found out the link.
Your paper, which I talked about in the introduction, begins with a problem that many professionals recognize
Mhm.
now,
Yeah,
and that's products can pass validation but still underperform in the field.
yeah.
What's your hypothesis for why that gap exists?
Yeah, exactly. Like, so whenever you are trying to create a test case, right? So, so what basis you are trying to create test case? Are you creating based on just a DFMA, or just field failures, or just a P diagram or FPD, or based on like service or operator manuals? So we should need to identify like what basis we are creating the test cases. right? That is the main important thing. So if you are just creating based on just one parameter, no, that is not useful. You will get like n number of test cases. So is it possible to test all the test cases within the within available time? So you cannot test every test case, right? So, and also like if you are putting like, so if you are adding so many assumptions to the test case, so we if something is happened to the product, do you know which one is which one is causing the issue? We don't know, right? So that's where some lag is there, or some gap is there. So so whenever we are designing the test case, we should at least have two parameters and up to five parameters. So
Yeah.
you should choose at least two, and max we can go for five or four or five. So which will help to find out like which one is which one is giving the what what can we say, which one is giving the failure mode, or which one is causing the issue, and those kind of things.
So, based on your recommendation of 2 to 5
Yeah,
cases,
yeah.
what do you think are some of the common reasons lab testing misses real world failures? Are they looking at too many cases? Are they looking at too few cases? Are they not looking at the right cases? What's
I
your
mean,
take on that?
so I mean, it's hard to predict. Like it's a maybe based. It may be based on like how the product is experiencing in the customer side, right? That is one thing, and how customer is using it, right? That is, I mean, I can say like some of the misuse kind of testing. So we do at some level, but we may not do at a full extent, right?
Yeah.
So those kind of things may be causing the field failures which we haven't seen in the lab environment. Yeah,
In your world, in our world, there's a lot of DFs, DFM, DFR. In
yeah,
this case, I'm going to ask you about DFMEA, which is
mhm,
design failure mode and effects analysis.
right.
What does DFMEA do well, and where
Mhm.
does it fall short when designing reliability tests for complex products?
I mean, most of the times it's useful, I would say
Hmm.
that, because we are taking so many inputs for the DFMA, which means like, for example, we understand the product better, right? In order to start the DFMA, we need to understand the product better. We should have a functional block diagram, so which will help you to understand like what are the components, what are the interactions between the components, and what are the functions and requirements along with it. And we also create a p diagram, parameter diagram, which will help to understand like what is the input, and what is the system, and what is the ideal function of it, and what are the noise parameters, and what are the control process we are taking into the consideration. So these and all are the inputs to the DFMA. So whenever we are writing the DFMA, divide we divide the system into subsystem into components, and the components we write the function of each component, and we write the failure mode, and we write the cause, we write the effect, and those things. So since we are covering all these things, so I don't think most of the failure modes we are covering in the DFMA, most of the things, I would say that.
Interesting.
But it's, as we said, like, so DFMA is not, static document, right? So it's a live document. So we use DFMA document all over the life cycle of the product, including the field monitoring also. So whenever we see some, failure in the field also, we consider and we document in the DFMA, and we make some design changes or process changes or whatever happening, causing that issue, and then we do the testing again, and we move forward.
The difference between DFMEA and other tests is DFMEA is really more of a living document for the life of the
Live.
product. It's constantly being updated, and resulting sometimes in retesting and another look at how it's made. Where a lot of other tests are pre-ship tests, so they're kind of test it, forget it, test it and forget it. It's
Yeah,
done, right? So
yeah, exactly. Yeah,
DFMEA is constantly being evolved and
right.
improved based on the legacy life of a product, maybe unintended contextual operating environments, maybe all of a sudden one part is deployed into a harsh environment that wasn't intended when the product was
Yeah.
designed, that might be fed back into DFMEA.
Sure.
You have quite a few proposed frameworks. And your proposed framework brings in tools like parameter designs, functional block diagrams, interface matrices, field failure trends, usage patterns, service information, consumables, and manufacturing data. Said all that in one breath. That's a lot of
Consolidation.
framework. Why is it important to bring all of these inputs together?
So that is the thing, right? Like, so we don't know, like, so where we can see the failure mode. So we cannot grab all the failure modes in DFMA, for example, right? So if we are talking about some of the usage patterns or service or operator manuals, so those kind of things we cannot directly implement in the DFMA, right? So those kind of scenarios, we have to have we have to consider like so many other parameters as well to to see the experience, to see the real experience of the impact, or real experience or the impact of the test case what we are doing should be reflected in the field. So that's why I'm considering like just not like DFMA, just not field failure data, just not P diagram or FPD. So we should consider everything, so and blend together and make sure so we are testing the right test case and make sure it should reflect should be reflect in the actual field. So yeah, that's what I said. Like, so DF we cannot include like operator or user manual or service manual things related test cases in the DFMEA. So we should consider everything so that we'll have fruitful test cases in order to have a better reliable product.
This next question really stems from an issue we had. We're an equipment manufacturer within the electronics assembly space, so we're part of the circuit assembly manufacturing ecosystem. And when in the early days, when we were designing our equipment, we would design it with the intended use in mind. Well, this is what they're going to be using it for. This is the climactic in-use environment. It's going to be used in a controlled, humidity-controlled, temperature-controlled environment, like a lab. They're going to put certain types of chemicals in it, which we're all aware of. We all know, how to handle those chemicals. And then you get a customer that didn't read that part of our thoughts, right? They're doing something we never expected. They're pushing buttons out of sequence that we never expected.
Sure.
So you make a distinction between testing from the engineer's point of view and testing from the end user's point of view, which is what we had to start doing. What changes when test designers start thinking like users rather than engineers?
Yeah, so as I said before, like so we should generally, as an engineer, if I want to do the testing, right? So what I look is like I go for any of the standards and I look for the failure modes, and based on the failure modes, I come back and design a test case. So that is the engineering point of view. But are we really testing based on the usage pattern? No, right? So we are checking some random failure mode from a random standard and coming back and creating the test case and testing, do the reliability testing. And if it is, we don't know, like if, for example, we pass the test and we release the product, but we are missing the actual product usage, right? So yeah, so we may see the failure in the field during the usage. So that's where I was putting in the paper saying like, so we should test in the engineering user point of view rather than the engineer point of view, basically. So here we are including everything. So we are including service manual and operator manual as well. So we don't know like whether user will follow the instructions, user manual or not. Whether service person use the service
I can
manual.
tell you firsthand they won't.
Yeah,
That's the
exactly,
first
right?
assumption that we now make. I'll
Yeah.
tell you an anecdote. In the early days of my company,
Hmm.
I did a lot of things. I did sales, I did service, all the things that
Right.
when you start up a company out of your
Hmm.
garage and you start slowly building it, you're doing everything. And
Yeah.
I am not a reliability or a test engineer. That's not
Hmm.
my forte.
Sure.
But I've got a lot of common sense,
Hmm.
analytical minded. So
Yeah.
when a when a machine would do something it wasn't supposed to do, the
Right.
way I learned to diagnose
Hmm.
problems in my simple
Hmm.
brain is okay, what if I intentionally tried to make the machine do that thing that
Hmm.
it's doing that it's not
Yeah.
supposed to do? What would I have to do to cause the machine to do that? And then I start looking there. So I remember going out into the field and the machine was doing something. I forget. I think it was like
Hmm.
overflowing with water. Build cleaning
Sure.
machines, and and there's only a handful of causes that can cause that. One of them is a float switch, a sensor that detects when
Sure.
a certain tank is full. The sensor must be
Yeah.
bad. Nope,
Hmm.
sensor's good. Okay, there are solenoids that turn off and on. The solenoid must be stuck open. Nope.
Right.
It's perfect. We 100 cycles in a row. Could not make it fail. And a few other
Okay.
things. And I started thinking, well, if I were to try and duplicate this problem, if I were to try and make the machine overflow, whatever the case was,
Right.
I would have to disconnect the float switch or
Right.
put a bunch of debris in my incoming water line so that the
Hmm.
solenoid diaphragm would get stuck on this debris and whatever. And I'm like, that's the only way I can think of making this particular event happen. And I told the customer that. And he goes, well, what do you consider debris? Like, scary question, but anything that you don't expect to be circulated around the machine that's not soluble, that doesn't dissolve, that gets caught up in
Hmm.
the plumbing. And he says, like raw solder paste? Like, yes, that would do it. And I'm like, but this machine is not designed to clean raw solder paste. It's designed to
Right.
clean post reflow assemblies where all the solder
Sure.
paste has been melted and is
Hmm.
stuck to the board. I mean,
Yeah.
he goes, well, we throw misprints in there. Like, okay,
Yeah.
no solvent, no chemical, no water
Hmm.
will dissolve
Hmm.
spheres of solder. They're all
Sure.
going to accumulate in the plumbing. Just like if you just eat too many cheeseburgers for a lifetime, your arteries are going to get clogged up. That's what
Yeah.
happened. And but we never thought that
Hmm.
someone would put, you know, illegal from our point of view, illegal things in the machine. So we had to go back, not through a formal DFMEA, but in a very informal tribal version of that. We had to go back
Yeah.
and design special filtration systems within the machine to account for things that we did not allow in the machine, right?
Makes sense. Yeah.
So problem solved. But that was
Yeah.
something we didn't think about when we were designing the machine. It's like, well,
Sure.
no one's going to put this in there. They're not going to clean their dishes after lunch in the machine, although
Yeah.
they have. But now you get a clogged filter. You don't get a overflow in the floor.
Yeah. That's
One of the
something.
ideas in your paper is that
Hmm.
system level failures often come from interactions between variables. We're all pretty good about testing variables, but then you
Right.
start combining variables, and now
Right.
the the potential causes just rise exponentially, right?
Right.
Huge combinations. Can you explain
Yeah.
why testing one variable at a time may not reveal the most important failure modes?
Yeah, like so. I mean, the purpose of the test approach is like so. We should have a minimum of two and a maximum of 4 or 5 parameters. So if you are just testing the one parameter, so do you have that much of time to test all the parameters, all the test cases? So if you want to launch the product, right,
Right,
within like next 2 years, so
right.
you if you
It'll never make it to production.
yeah, so we don't know like if you started to test each and every test case, it will take forever. I don't know like it will generate like I mean, it will generate helpful insights or not. So if you are combining one or two, I mean at least two parameters, then it will, for example, right? If you take like infusion pump, so if you are combining one parameter from DFMEA, one parameter from usage pattern, so that you know what you are looking for in the DFMEA, like actual function failure mode of the particular component, and also like how user going to use the product with that component. So if you're combining both, like you are testing like which will make sense. So if you are testing or if you are combining both parameters, it will help you to creating the meaningful test case, which will help you to test the product as well as the uh, which which will help you to test the product in the user perspective. So you are just not only testing the product, you are testing in the user perspective. So yeah, so if you are combining like two or three or four parameters, which will help you to generate like meaningful test cases, and which will help you to more focusing on like what will happen in the field rather than just what is happening in the laboratory. And also like it will help you to test the actual actual phenomena rather than your rather than just not testing the product. So we should consider like two or three or four parameters. Yeah.
I think that's quite analogous to fishing. If you're
Yeah.
fishing with a net,
Yeah.
and the net is this wide, 10 feet wide,
Yeah.
you're going to catch a certain amount of fish. By adding more variables, you're basically trolling with a larger net. And
Right.
to the point where if you do too many, you need a bigger boat
Yeah.
to drag
Sure.
that size of net.
Yeah.
So it's probably a bit of a compromise between having enough variables
Yeah.
and making sure you don't have too many, making sure you don't have too much, kind of the Goldilocks, the perfect porridge,
Yeah.
scenario where it's just right. At some point, you start adding too many variables. It's probably diminishing returns because then you'll never ship
Sure.
something, right? So,
Yeah.
so your recommendation is not less than two, probably not more than four or five.
Yeah.
Yeah, that makes a lot of sense from an optimization standpoint and from a
Sure.
realistic standpoint. You use the example of a multifunction printer
Sure.
and combining things like paper size, paper type, job length, and user cancellation, user input, maybe unexpected user input.
Right.
What does that example, you chose that for a reason, what does that particular example teach us about creating a more realistic test case?
So like, so everybody uses the printer as you mentioned, right?
Right? We're all
So
familiar
like,
with those, for better or for
yeah.
worse.
So
We're all familiar with printers.
yeah. So like, so whenever we are writing the test case for the printer, so we have to see like different aspects, like as we talked earlier about the approach, right? So we have to take different input parameters like p diagram, fbd, dfmea, and usage pattern, and other things. So when we are creating a test cases for the printer, for example, right? So you will get like for example, if you take just a p diagram, so you will get like 100 action items. fbd, you will get like 50 action items. And if you say take dfmea, you will take tons of action items. So we get like different counts of action items from each parameters. So we need to see like how many of them are unique, right? Some of them are like copy of other one, or something very close to that one. If you test this one, you can reveal that one as well, right?
Right.
So 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 based on this, like we need to identify like unique action items
Right.
from each
So let's
parameter.
say in this example, the scanner portion of
Yeah.
the printer and the printer
Right.
portion of the printer.
Yeah.
Two completely different sets of technology. One is optics
Right.
and character recognition, maybe, optics, and the other is ink on paper.
Right.
Two very different
Yeah.
tests because you're not going to
Right.
test the whether the dot pattern is printed
Yeah.
in the right place when you're concerned
Sure.
about the scanning portion of it, right? You're not going to
Right.
test the lens quality
Hmm.
to determine, why the yellow keeps getting clogged up in
Right.
in a
Yeah.
colored printer. So yeah, I see your point. So multifunction, if people are building multifunction devices, which we tend to do with electronics more than ever,
Yeah.
those are more variables, not
Sure.
just human interface variables, but those are real production variables and test variables
Yeah.
because there's so many
Right.
different functions within one product, and you probably have different FMEA protocols for each function of one
Yeah.
machine. Yeah,
Yeah.
that can multiply out pretty quickly.
Right. So like we talked like so each one is generating hundreds of action items. So we cannot test everything. So we need to find out the unique ones, and also we need to club together. So
Yeah.
we have like for example we have like 300 or 400 unique test cases count. So then we need to divide into like so test case matrices like so 3 to 5 contains like 50 to 20 200 job range, right? 3 to so we need to divide like 3 test matrices, and we need to divide all the action items and move on the relevant test matrix, and then we test based on the test matrix. So we test matrices. Yeah, so this is the thing, right? Like so people will generally confuse between test matrix and test case, and so people think test matrix is something different, unknown. So it's basically a test case. So it's a bunch of test cases come undergo as a test matrix. So we test the test matrix, and we test different test cases under the test matrix. Yeah.
Again, I'm not a reliability expert, but I know that for the sake of this question, there's a million tests out there, but for the sake of this question, there's two types of tests. There are tests that test whether a product will work within a certain range of, let's just say, temperatures, just as an example.
Right.
And then there are tests that find out where the breaking point is.
Right.
How important is it to not just test within the expected operational conditions, but actually break a few parts intentionally to find out how close you are? Let's just assume that the printer, let's go back to the printer. The printer prints beautifully well when the ambient temperature in Fahrenheit terms is between 35 degrees and 87.
Right.
And we test it in those environments because no office is 35 degrees, no office is 87
No.
degrees. So that seems like a fair number. So we test it. And the
Right.
humidity is, 35 to 60%.
Right.
And it tests beautifully in those conditions. And then
Yeah.
someone buys the printer, they take it out to a safari in Africa. It's now 104 degrees and the humidity is
Yeah.
98%, and it
Yeah.
fails. So
Sure.
how important is it, at least for some limited testing, to understand where the breaking point is? What is the actual physical limit of a part, so that you don't mistakenly think, oh, this is going to be good, but you're actually 2 degrees away from it failing and you never saw it because you never tested for that. Does that make sense?
Exactly. Yeah, that makes sense because so when you see so we do this kind of testing mainly for the electronics, right? You know very well about electronics. So if you take PCBA, so we know for example, we operated the maximum temperature inside any housing or whatever the component. We say it's a 50 degrees Celsius, right?
Yep.
So, but the surrounding temperature is ambient generally,
Yeah.
but so what we do is we do accelerated life testing, right? So we test it generally, we don't test at the nominal temperature. We elevate the temperature where um, without damaging the parts because of our stress level, right? So we elevate the temperature to where the PCB or the component on the PCB or the printer, whatever, can withstand. And then we apply the stress and reduce the cycle time, and we perform the test. So this is mainly for like to demonstrate the reliability of the product, or to understand the useful life of the product. And also like we also need to do highly accelerated test for some cases to find, as you mentioned. So if you operate at whatever 101 degrees Celsius or whatever,
Yeah. That's
it
the
will
fun
fail.
test. That's where you get to break things.
Yeah, exactly right. So if you perform like highly accelerated tests, we don't know. Like, so if we are operating, for example, the maximum temperature for the particular component can withstand is like 90 degrees Celsius, right? So if you are elevating the temperature, you are testing for something else which you don't know, right? You don't know the failure mode what you are looking for, but you are going to test at higher temperature to find out the design weaknesses and make sure we can modify our design a little bit to withstand the particular temperature. And then we do the testing and release the product. So as you mentioned, so if you're testing the printer, if the usage condition at some desert or whatever is 104 degrees or 105 degrees, but our product is designed for 80 degrees Celsius,
Yeah.
so we need to have some test cases like that to make sure we are testing out of box conditions or misuse conditions or
Yeah.
harsh environment conditions and so on. Yeah.
Right. Well, that also, it's not only to test to make sure it can operate in those misuse conditions, because no one really
Right.
puts that type of reliability in a part, but
No.
it does help document the failure mode so that when a
Sure.
part comes back on an RMA and they say, oh, no,
Yeah.
we ran it in a cooler. No,
Yeah.
because
Right.
the
Sure.
diagnosis is consistent with
Yeah.
this particular part was exposed
Yeah.
to temperatures beyond its operating certification, right? Its
Right.
specification.
Yeah.
Your paper discusses something which I think is really important, not just in reliability, but in any kind of testing, and that's closed loop processes where field data continuously improves future test design.
Right.
What should that feedback loop look like inside an organization?
Okay. So this entire methodology is data driven, right? So which relies on like multiple input sources, as we mentioned. Each input is associated with several parameters, and which are continuously updated based on the insights from various sources like field failure data or the lab test data or from the manufacturing, or if you are taking the data from the legacy product. So these test cases initially are derived from the parameters available at the state of art process. But over the period, what happens is like additional parameters are incorporated as a new data becomes available. So for future products, all learnings from previous products are integrated into the test case design. So when test cases are like moving forward with like multiple products, or the correlation with actual field performance increase significantly, often reaching up to 95%. So that is a closed loop. So this iterative approach makes sure that test cases remain relevant, comprehensive, and the predictive to the real world conditions. So for example, if you take one legacy product which has like 4 to 6 parameters, and which has like 60% in the reliability, and if you move to the second product and you consider like 7 to 12 input parameters, which will help to which will also include like what are the field learnings, what are the test learnings, what are the service learnings, what are the manufacturing learnings, and so those can be incorporated in the test cases for the product too. So which will yield about 90% of the correlation. And so the if you are testing the next generation of the product, if you incorporate learnings from the product 1 and 2, so you are achieving 95% of the correlation. So that's where like, so it's all about learning from the from your legacy products and the previous products, and the learnings from your field failures, and the learnings from your service prospective failures, or anything like that. So it's more of a learning, like, so if you are I mean, so it's kind of a machine learning, right? So you are training the machine from your inputting a different or if inputting all sorts of data, so that it will react accordingly and those kind of stuff. So yeah,
We have the ability today to collect large amounts of data. In some
right,
cases, too large for our own good, because that's how you get big data.
right,
Millions and millions and millions of data point. No
sure,
human can discern all of that.
yeah,
However, AI can. What's your
right,
take on using AI workflows and things like that, building agents specifically to
sure,
analyze data, to spot trends, to
right, yeah,
create hypotheses,
hmm,
and guide the reliability engineers into, look here, don't bother looking there. Here, this area is our
right,
problem.
yeah.
How, first of all, has AI already infiltrated into your level of expertise, or is it coming? Is it being received with open arms? Is it being received skeptically? Tell me about the AI world in terms of reliability.
I mean, so AI is useful in some kind of data handling situations. For example, right, you deploy a product to the field, and or just not one product. If you are deploying like 5,000 of robots to the field,
Right.
so right, so you cannot manually check everything, right?
No. Big
So
data. Too big. Yes.
yeah, too big data. So in this kind of scenario, like we select some of the parameters, for example temperature or the current or the voltage or the resistance, those kind of parameters we monitor regularly, and so that it will help to understand what's going to happen next, right? So it's kind of predictive analysis. So we know like the battery health is like 60% or 50%, so we need to change the battery, or what is something is happening in the battery, some thermal management issue is going on, so we need to change the battery. So those kind of indications we'll usually get from like using the AI and ML kind of things. So I think it is very helpful if you are talking about large scale products. So but at the end, so the human or the reliability engineer has to take the decision and what to do next and what we can implement and where we are lagging, what kind of predictive analysis we are doing it, and how we can help make do the preventive maintenance intervals, and where, and if it is something related to design also, it will help to make the changes in the design, those things. So yeah, so it will help in handling the large set of data, so which human cannot handle. So but
Yeah.
at the end, human will be the person, who can take
Ultimately.
the,
Right.
yeah, take the
Right.
action, yeah.
Results show a significant improvement in lab to field correlation when more real world input parameters are included.
Right,
What should reliability teams learn from that improvement?
as we discussed in the beginning itself, like, so if we are testing something which is from the handbooks, or if you are thinking that can be happen or something like that, so those kind of scenarios, if your test also, if you are not testing at the right, right environment without right environment conditions, then if you are testing something else and you are getting something else, and you move on and you launch
Right.
the product, then you see the failures which are very relevant to the user environment. So those kind of things we miss in the we miss in the laboratory testing. So we should, that's why, like, so we should test in the user perspective rather than the engineer point of view, or just take some random failure mode or random test case and perform the testing and get the result. And if it is pass, it's good. If it is fail, everybody's mad at you, right?
Right. Well, here's an example of an electronic product that failed miserably after it
Right,
was deemed perfectly reliable. The early
sure,
days of LED lighting. I
right,
don't know if you remember when LED lights first came out. The
uh-huh.
promise was you buy it once. They were super expensive back in the day,
Right.
but they last, quote, forever, right? They'll
Right.
last
Yeah.
forever because there's no filament burning like in an incandescent
Yeah.
bulb. They'll last
Yeah.
forever, and draw a fraction of the energy and stay cool. Blah 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 blah. So I remember buying some of those early bulbs. Like a bulb was like $25, where an incandescent was $1.25, right? So there was
Right.
huge multiple there.
Right.
And then the idea started taking off and getting implemented around the world. And this was a problem specifically with very industrial cities in India, of all places, where there
Yeah.
was a lot of sulfur in the air. And
Yes.
the backing material on some of these boards was silver. And
Yes.
the result when silver, mixes with sulfur is
Right.
tin whiskers. All of a sudden, these things started failing. The light started flickering. The light started getting
Sure.
dimmer. They started failing in huge
Right.
numbers
Yeah.
only in like very industrial places where there was high degrees of sulfur in the air. And this was also back in the day when air's not as clean in any city than it is today.
Sure.
But I can imagine the reliability engineers back at, I don't know, GE or Philips or whoever made the bulbs back in the day, were
Right.
like, we don't understand. We don't grow tin whiskers here. We have no migration issues, corrosion issues here. Why there? What are they doing? What are you guys doing? In India?
Yeah.
Well, nothing. They're only guilty of screwing the bulb in. That was it.
Sure.
And turning it on. And the rest was chemistry, right?
Yes. The
and-
user environment is different. Yeah.
Right. But who would think about, hey, before we ship it, let's do one more test. Let's throw it in a sulfur chamber and see.
Sure.
I wouldn't think of that. They obviously didn't think of that.
not.
And next
Yeah,
thing you
of
know, the
course not.
entire industry had to come up with a different material that
Yeah.
was, impervious to sulfur-rich
Sure.
environments, things like that. But that to me is a perfect poster child example of factoring in real-world conditions, because we build products in a controlled environment. We frequently test products in a controlled environment. And then they go
Right.
out into the Wild West, right? Where they're dropped, they're exposed to harsh chemicals, they're exposed to harsh temperatures, harsh humidity conditions, all sorts of crazy things that humans do, stupid human tricks that we do with our devices. And, they go where we go. And we go to some pretty nasty places sometimes. And the electronics, they're conscripted. They're coming with us. So it is challenging in terms of how ubiquitous electronics are today to test for every potential environment where people might be, or even where people aren't. Space, turns out, is a very challenging problem because they have extreme temperatures, super hot, super cold, depending upon how they're facing the sun. Radiation causes a big problem because it destroys chips and all these things we don't have to do in our lab that we have to do when things go into space or into, on people, in people, with people, all of that.
So that is also one of the things, right? Like, so when you don't test in those kind of environments, and then you launch the product. So then customers started to report the issues based on these symptoms and those things. So then you come to know, like, so okay, this is happening, right? So then you try to test those things, and if you want to make some design changes, or if you want to add some extra paints or whatever, right? So you can do those modifications and you validate, again you launch the product. So those are the learnings from the field, so which will help to incorporate with your test case, so which will be more efficient.
So I'm going to give you a promotion. You're now a business owner. You've come up with an idea. You've designed a product.
Right.
You've left your company now. You've started your own company, and you're building a widget. But you don't have a lot of money. You're underfunded, like pretty much every startup is. So for companies like that can't afford a large reliability team, a lot of expensive test gear, where's the best place to at least start? For people who aren't doing it now, for you when you're just starting up, what's the first bite at the apple look like?
So what would think as a reliability engineer is like, so I would, yeah, so yes, I don't have much time or the money to test each and every test case or the failure mode. So what I would do is like, so I look for like severity, so which one is the more severe, which one is um, which one is causing the safety risk, which one is creating a customer dissatisfaction, so which one is essential, right?
Where's your
So
biggest pain point, right?
yeah, so
Yeah.
I would choose those, those parameters or those areas to create the test case, to make the product survive and work as intended in the field with
Mhm.
customer satisfaction, with less safety risk to the customer. So yeah.
The saying goes, how do you eat an elephant? And the answer is one bite at a time, right? So take the juiciest
Yeah,
bite. Take the bite that solves the majority of the problems, or at least
sure.
not the tiny ones, and then work toward the least
Yeah.
possible ones.
So including the safety things, we also need to careful about like downtime reduction. So that is the other important thing. So if something is not working and the customer need to do it, if we are wasting customers time too much, no, it's not that good for the product or the company, right? So we should carefully select the test case which will impact the downtime of the product as well. So that is the other concern.
Yeah. What you've been in, you work for companies, right?
Yeah.
Aerospace, medical,
Yeah.
you've been around. What advice would you give to reliability engineers or people, concerned about reliability who want to
Mhm.
move their organizations from a we pass the test mentality to we understand field behavior mentality? What's your best advice to influence that culture change? Because it is a culture change.
So it's basically like it's a vary from company to company, right? So if that reliability motivation is coming from the top management, that would be, that would be helpful to the organization. Basically, if it is going from the down to the top, then we need to have so many buy-ins, right? So if your top level management is not encouraging the reliability program, or it's just like a number sake or the namesake, that's not useful anymore. So it should come from the top management, so that it will be help motivating the other people in the organization, so that we should have a good reliability plan or the program. And so if we have a good reliability program, we have so many different approaches to have the better reliability product, which will help to, which will help to launch the product in the field with good customer satisfaction, and also like very good reliable product. So that kind of culture has to be developed from within the organization, so that we should have better approaches and better plans and better products.
And for executives at companies
Right.
who don't really embrace what you're
Right.
saying,
Yeah.
I would encourage them to study a case history of Boeing, the aircraft
Right.
company,
Mhm.
that went from formally a quality first, reliability first, customer first, safety first
Yeah.
culture,
Sure.
and then merged with McDonnell Douglas. They bought
Mhm.
McDonnell Douglas, but inherited the McDonnell Douglas culture of shareholder first and profits first.
Okay.
And
Yeah.
we've seen in the last several years, between the 737 MAX, between the early problems with the Dreamliner 787, between
Sure.
the MAX door plug issues where doors are blown out, the door blew out of
Yeah.
the plane, to the 15-year delay in certifying the 777X. That's what
Yeah.
happens when quality and reliability are put secondary
Yeah.
to numbers, right? And I'll
Yeah.
bet all the executives at Boeing today wish they could rewind the clock, because
Right.
it just costs them immeasurable amounts of
Of course. Right.
stock value and reputational value. Stock
Yeah.
value can recover. Reputational value is
Yeah.
generational. Pilots who don't trust Boeing today, you'll have to wait for their children to become pilots. And even half of them will remember what mom or dad said. And it's going to take a couple generations for that to be restored. And that was simply a refocus, no less effort. They put all the effort that they were putting into quality and reliability, and they redirected it to profit and stock value and shareholder value and dividends, buybacks, all this stuff that made them look really good on paper until they started killing people. And you can't get back from that, not quickly. So that's a radical warning, but I think it makes a lot of sense. And, the irony is, before the merger, Boeing stock was doing fine. They figured that quality, safety, reliability first, shareholder value comes as a result of that.
Right.
The chasing the money had a negative effect on the reliability. You do not get both. It's not win-win. It went from win-win to win-lose. To win-lose and then lose more, ironically. So, So I think we cannot underestimate reliability. That's one of the reasons this show exists, so I can talk to fantastic people like yourself that are subject matter experts, all in various parts of the assembly arena to make sure that we're building products that are more reliable than they ever have been in the past, because electronics are more ubiquitous than they've ever been in the past. They're more central to our safety, our health, our communication, our transportation, our entertainment, everything than they ever were at any time in the past. And it's just going to get more ubiquitous, right? So now is the time really to focus on reliability. Now's the time to implement these systems. Now's the time to use the tools that are emerging at record speed, I'm thinking AI in this case, to assist us in that process. And I think with the AI tools alone, the costs of implementing and discerning all that data and coming up with actionable insight is much lower than it used to be. Because before it would take hundreds of engineers to comb through all the data to spot a trend that AI, an AI agent can do in 4.5 seconds. So
that is true.
So I think it's easier, and it's more urgent than it's ever been in the history of electronics. So
that is true. I remember using AI for derating for one of the PCBA. If you want to do the derating analysis for the PCBA, you have thousands of components. You want to do the derating for each and every component. It takes forever, right?
Yeah.
So if you use the AI, and we have all the information required for all the components. So we have information regarding the resistors, capacitors, whatever. So AI knows everything, right? So it will do within 2 hours, right? If the human want to perform, it will take at least a month.
And once the prompt's designed and once the data is already in, it's seconds after that, right?
Just calculation, right?
Yeah. Well, Dr. Nishith Gorla, thank you. This has been a great conversation. I really love talking about reliability, and a lot of times when I'm talking to my guests, they're connected to reliability a little bit remotely. You are directly connected to reliability. You are Mr. Reliability. So thanks for doing what you do. Thanks for sharing what you do with me and my audience. That paper was great for my audience who would like to read that paper that was published recently. I'll have a link to that in the show notes. If you're watching this on YouTube, look right down here, right below me. It says See More, and you can click that, and there'll be a link to download that article directly from the magazine. And if you're listening to this on your favorite podcast app, look at the show notes on your favorite podcast app, and that information will be there as well. Thank you so much, Nishith, for being my guest. I really enjoyed the conversation.
Yeah, me too. Thank you so much.
And that's a wrap on another episode of Reliability Matters. Thanks for being part of our Reliability Matters family. Whether you listened on your favorite podcast app or watched on YouTube, I really appreciate you being here. If you haven't already, hit that subscribe button so you don't miss future episodes. A big thanks to PCB Chat from the Printed Circuit Engineering Association at PCBchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Got a question or an idea for a future episode? We'd love to hear from you. Visit reliabilitymatterspodcast.com. Thanks again for being here. Until next time, keep learning, keep doing it right, and remember, reliability matters. I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.